Hello, my name is Daniel Song, and I'm going to introduce about lattice-based airless ball architecture for enhanced athletic applications. Sports ball haven't fundamentally changed in over a century. This project eliminates the pneumatic bladder entirely and lets 3D printed TPU lattice geometry replace air pressure. Three failure modes define the problem: gradual pressure loss, catastrophic puncture, and sensitivity to temperature and altitude. Wilson's airless Gen 1 proved commercial viability, but systematic academic study of lattice geometry's effect on bounds simply does not exist yet. Four research questions structured this work, covering hole geometry, optimal porosity, grip performance, and sustainability. Each hypothesis is grounded in structure mechanics. Three variables were tuned: hole shape, hole size, and porosity. On-shape ensured dimensional accuracy, while Blender generated perforations procedurally. Mass was iteratively matched to MV specification because incorrect rotational inertia undermines performance regardless of bounds equality. TPU's elongation at break, 300 to 700%, dwarfs PLA and ABS by an order of magnitude. That difference in compliance is what allows the lattice shell to compress and rebound like a pressurized ball. Drop tests at 4 height captures how TPU stiffness shifts with impact speed. Friction testing uses curved hemispherical specimens rather than flat material, preserving the real contact geometry that governs the grip. Hexagonal medium porosity configuration approach the conventional basketball's COR reference line, while circular geometrics fall short. Hexagonal cells distribute stress uniformly, whereas circular holes concentrated at edges, dissipating the energy as heat. Below 30% porosity, the shell is too rigid to store energy, and above 60%, it collapses. The 40 to 50% window is where compliance and structural integrity balance optimally. Solid state mechanics have no pressure to lose. Altitude, temperature, and service time become irrelevant to lattice performance, which carries meaningful implication for professional equipment standardization. Flat TPU undershoots rubber grip, but lattice perforation compensate by increasing effective contact geometry. The structural design doubles as a traction system. A bladderless ball never requires reinflation or replacement, extending service life and reducing waste at scale. Consistent with ISO 14040 life cycle assessment principles. All results remain theoretical. Lattice porosity allows air to pass through the shell, altering drag and the Magnus effect during the flight. CFD modeling is essential before claiming full aesthetic equivalence. A hexagonal lattice at 40 to 50% porosity is theoretically viable as a pressurized ball replacement, offering consistent bounce and reduced environmental impact. Empirical testing and CFD characterization are the essential next steps. Thank you so much.